In this video we're going to look at subnetting, and this is an area that most people struggle on, and hopefully this will try and clarify a few issues for you. Basically, IPv4 has 32 bits in the IP address field, and the IP address is divided into two portions, the network portion and the host portion, and I've shown these here in red and blue. The borderline can vary, and basically this is determined by the subnet mask, which determines which part is network and which part is host. The network is a bit like your area code for a telephone exchange, where the host is your actual individual phone number. So think of it a little bit like that. Basically all devices with the same network address, the red part, are on the local network. If the network address is different, they are on a remote network. There are three different address classes that you should know. Now, address classes are no longer used, but they are legacy and they're still in the Cisco material. A, B, and C. The first octet of the IP address will determine which class the address is. Class A is any address between 1 and 126. 127 is reserved as a loopback address. Class B is any octet between 128 and 191, and Class C is 192 to 223. Now the differences between these are the borderline between the network address and the host address. On Class A, the first 8 bits are network and the last 24 are host. With B, it's 1616, and with C, 24 bits are network and only 8 host bits. The number of host bits determine how many hosts we can have for each network. So subnet masks are also 32 bits, and they're written in dotted decimal format, just like IP addresses. They're basically used with the IP address to determine which part is network address and which part is host address. A binary 1 means the corresponding bit in the IP address is a network address, and a 0 means it's a host address. So these all mean the same thing. This is how we write a mask in binary. So basically what this means is all these ones here up to this point means the network address finishes at this point, and the host part of the address is all the zeros. This is the decimal equivalent of this, 255.255.255.0. All we're doing here is dividing this 32 bits up into chunks of 8 bits and then putting dots between them. So 255 is just all these binary bits converted into decimal, and then we put a dot between each one. The 0 obviously means these 8 zeros at the end here. The other way of writing this is prefix notation, and basically this just counts the number of binary 1s in the mask and puts a slash in front of it. So slash 24 means there's 24 binary 1s. That's the shorthand way of doing it. In IP version 6, then that's the only way you don't use this method. Now you should know your binary conversion between decimal and binary. Basically it's powers of 2, which double each time, so 1, 2, 4, 8, 16, 32, 64, 128. They're your 8 bits, and you add the numbers up that have 1s underneath. So basically write down the numbers above, convert from decimal to prefix. You can use the dots as a guide. So for example, if you wanted to convert 255.255.250 to slash 24, the first 8 bits are 255, so that's 8. The second 8 bits 16. The third 8 bits are 24. There's no bits here. The second one, 255.255.255.248. Well, what's that in a prefix? It's slash 29. That means there's 29 ones. How do we work this out? Well, there's 8, there's 16, there's 24, and the final bits are 248, which is 128 plus 64 plus 32 plus 16 plus 8 gives us 248, which gives us slash 29. And we can do this the other way as well. We can take any mask and with a slash or prefix notation and convert it back into a mask. basically we can use the table to figure out the mask. Now for a particular network, we have two reserved addresses. One of them is a network address, which is always the first address in the network here, and we have a broadcast address, which is always the last address in the network. Anything between that is called a host address, and only these can be applied to interfaces such as PCs, printers, default gateway on the router, and so on. The network and the broadcast are reserved. The network represents all the addresses in the network, so we usually use that for things like configuring routing protocols, and the broadcast address is used to transmit to every device in the network at the same time. Subnetting and address space. There are two ways of subnetting. The first one is fixed length subnet masking, where basically you're chopping the address space up into blocks that are all the same size. So basically what you do is calculate the largest block first and then make the others all the same size. The second method is VLSM, or variable length subnet masks, which basically is more efficient because it uses address blocks that are smaller depending on the size of the network. So it makes more efficient use of address space. So what you need to know is your powers of 2, starting from 0 up to whatever value you need. Remember, these values are just doubling each time as you go from right to left. The ones I tend to remember are 2 to the 0, which is 1, 2 to the 5, which is 32, 2 to the 10, which is 1024. And if you know those three, then if you want to go this way, you just double the numbers. If you want to go this way, you can halve them, and so on. Halve the numbers this way. And if you want to go further this way, then just double them. The other formula you need to know is 2 to the n minus 2, which gives us the number of host bits which are required. Sorry, n is the number of host bits in the address. The reason we have this minus 2 is because network and broadcast are reserved, and we can only assign this to hosts. So that's why we have the minus 2. There are 3 basic steps that you need to do for subnetting. The first one is to work out the network address and the mask for each subnet. The second one is to find the broadcast, and the third one is the usable host in the middle. We have an example here. We have some routers with some serial links in between, and each router, which is not shown here, has some LANs off it which have different numbers of hosts. And here we're going to use variable length subnet masks to divide the network up. We're given an address range of 172.16.00/16, a standard class B network, and we're going to divide this up per the host requirements to save as many addresses as we can. So 4 links here: Berlin to Paris, Paris to Rome, Rome to Kiev, and Kiev to London. These are these serial lines here. So what do? Well, we start off with the largest number of hosts first, which is Berlin, the top one here. And we use the formula 2 to the power of 8 minus 2, which gives us 254 possible hosts. So we're using 8 host bits. 254, is that enough? Yes, because it's more than the 250 that we need. So we're going to use 8 host bits. So if we have 8 host bits, then the remainder must be network bits, obviously, because there are 32 bits in total. This means we're using 8 host bits for the mask. Sorry, for the host portion. So the mask is going to be /24, because we have 24 network bits, or the equivalent of 255.255.250. So the network address for this Berlin LAN is 172.16.00/24. Now, all we do, what we want to do now is we want to know where Paris starts. We want to know the start of the next range. We've subnetted Berlin, now we're going to go on to Paris. Where we do that, very simple, we find the value of the last binary 1 in the mask to find the start of the next range. And this will basically gives us the amount the address will increment or the block size. What do I mean by this? Well, if we look at this mask, if we wrote this in binary, then the final binary 1, which is the last one here, would be the equivalent decimal value will be a 1. What this means is the equivalent octet, which is the third octet in the network address, would increment by 1 for the next start of the next range. Here we have it here again. So the last binary bit is set to 1 here, and this becomes a 1. And what that means is the network address increments by 1. So the Paris network address is 172.16.10. Do the same thing again for Paris. We need 120 hosts. Okay, so 7 host bits will be enough, because 2 to the power of 7 is 128, minus 2 is 126. So 7 host bits is enough to cater for 120 hosts. This means if we have 7 host bits, then the other 25 bits must be network bits. That gives us a mask of /25, or 255.255.255.128. So you can see how we're getting these masks here. All we're doing is finding the number of hosts and working on that basis. We do the same thing with Paris. We look at the mask, find the last bit value of the mask, which is a 128. So the next range will increment by 128 in the last octet, because we're here in the last octet. So the Rome address is 172.16.1.128. That's the start of the next range here. Now we work out Rome, which is 2 to the 6, because we need 50 users for Rome. So 2 to the 6 will give us 64. That's enough. Minus 2 gives us 62. That means there's 6 host bits, we can see here, which means the remaining bits must be network bits. That means 26 network bits. That gives us a mask of 255.255.255.192, or /26. Now if we go to the value of the last binary 1 here, it will be 64. So the next range increments by 64. That gives us a network address. If we add that on, it gives us a network address of 192. We do the same with Kiev. The number of hosts is 30. 2 to the power of 5 minus 2. 5 host bits gives us 30. That's okay. So 5 host bits means 27 network bits. 32 minus 5. There's our mask for that, and so on. Basically what this means is, for VLSM, we get this structure here, and as you can see, the block sizes differ depending on the size of the host requirements, whereas with fixed length masks we have the same size block for each one, which is very inefficient. There's also a quick method we can use for doing this, where we don't really need to do any binary conversion as such. Basically, get the subnet mask, calculate that, find where the block finishes, locate the octet with the last binary 1. Once you know where that octet is in the mask, get its decimal value. For example, 255.248.00 is a particular mask. So this octet here is where the last binary 1 lies. Do the sum 256 minus whatever value that is, 248, which gives us 8. And the next network starts at 8 above that. So, for example, if we start at 10.0.0.0, then the next range starts at 10.8.0.0.0.